9.1b, sequences and series. So what we're going to be talking about is summation notation. All right. So we need to talk about the notation of this. All right. This I is called the index of summation. Usually it's an I or an N or a K. It's usually those three. All right. I prefer N. However, you'll see I and K as well. This 1 is your lower limit of summation. That's where you start. Okay, this is where you start. And then this N is where you finish. All right, that's the upper limit of summation. And then this term right here is called your nth term, the ones that we've been talking about. That's your rule of a summation notation. Now, the difference between a sequence and a series is added up term to term. All right, it's a summation. All right, summation means you add. All right, sometimes it's called sigma notation because, you know, those Greek letters, that's a sigma. All right, so this first one, we have I equals 1 for my lower summation. I'm going to 5, and my rule is 3 times I. So the first thing we need to do is we need to substitute in my lower bound, and so I substitute in 1. So I substitute in 1. What's my first term? 3. And then I substitute in 2. That's my next term that I substitute in. So my next term would end up being 6. Plus, now I substitute in 3, and I end up with 9. And then I substitute in 4, and I end up with 12. And then I substitute in 5, and I end up with 15. And then I substitute in 6.
No. 18.
I don't want to substitute in 6. Why not? Because I stop at 5. All right. So now I need to add up all those together, and I end up with 45. Now, a lot of the times when we have a problem like that is I will actually bring out this constant multiple. I'll actually think of it as 3 times the summation from 1 to 5 of just I. And so when we do that, I'd end up with 3 times 1 plus 2 plus 3 plus 4 plus 5. Sometimes I like to factor out that 3, bring it out front, and so you can work with the numbers a little bit easier. All right? And guess what? You still get 45. All right? All right, let's look at part B. So this summation is going from k equals 3 to 6. So now I'm going to substitute in what? 3. So what's my first term? 10. And then I'm going to substitute in 4, and I end up with 17. And then I substitute in 5, and I end up with 26. I substitute in 6, and I end up with 37. And then I substitute in 7, and I end up with... I don't do that. Why don't I do that? All right, I end at 6. Now, one thing I want you to notice is before we actually even add these up, I want to talk about something. What am I going from? I'm going from 3 to 6. How many terms do I have? 4, but 6 minus 3 is 3, Mr. Flick. Why is it 4? Because I start at 3. I need to count what I'm starting with. All right? So I actually started at 3, so I would have 4 terms. So now if I add them up, and what do I get? I end up with 90. All right. All right, part C, this will require a calculator. This is actually a very famous one. We'll talk about it. All right, so this one I'm going to go from 0 to 8 of 1 over I factorial. So if I substitute in 0, 0 factorial is 1. So now I have 1 over 1, which is 1. And then I substitute in 1. So now I have 1 over 1 factorial, which again is 1. Plus, now I substitute in 2, and I end up with 1/2. And then I substitute in 3. 3 factorial is 6, so I end up with 1/6. Plus 1 over 4 factorial, which is 1 over 24. Plus, what's 5 factorial? Just multiply by 5. What do we get? 120. And then 6 factorial, which is 720. And then 7 factorial, 1,000, 5,040. And then 8 factorial, the last one, 1 over 320. All right. Do what? All right, and what do we get? 2.718. I'm going to go 28. I know we normally round to 4, but I'm going to go to 28 because it's easier to see this way. What number is that? Somebody said it. What number is that? That is E. All right. That is the number E. Now, this is a very famous proof of it. If I go from 0 to infinity, actually, if I keep on going forever and ever, that is actually going to give me the number E. All right. That is actually one of the proofs for that number. All right. All right. Of sums. The first property that I want you to notice, if I have 1 to a number of just a constant, all you have to do is multiply that constant by that number. For instance, on your homework, I'll even do it with you. On your homework, you're going to have something like n equals 1 to 4 of 10. What would that end up being? My first term would still be what? 10 plus my second term would end up being 10. My next term would end up being 10. And then my next term would end up being 10, which is 40. Or if you know this, it goes from 1 to a number. You just do 4 times 10, which is 40. However, it has to start at 1 for that to work. All right? All right, this is what we already talked about on our first example. If you have a constant multiple, bring them out front, okay? It's easier to work with, okay? You don't have to. It's just going to be, it's going to save you some time. And then on part numbers 3 and 4, you can kind of distribute your addition and subtraction to it. All right, you can take the summation of one part, add it to the summation of another, and subtract them as well. All right. If we have a finite series, what does that mean? It ends. It stops. All right? And so we can have a partial sum when it stops. It's a finite series. If it's an infinite series, it does what? It keeps on going. And it keeps on going, denoted by 3 or 4 little dots. All right? So it keeps on going on an infinite series. Okay? All right. So this first one, we're going to find the series from 1 to infinity of 3 over 10 to the power of I. And the first thing we're going to do is we're going to find the third partial sum. Do I actually want to go to infinity for a third partial sum? No. Where do I stop? At 3. So I'm actually going to do the summation from 1 to 3 of 3 over 10 to the I. All right. So I substitute in 1. Well, what do I get? 3 over 10. Plus, now I substitute in 2. So what do I get? 3 over 100. And then I substitute in 3, and I end up with 3 over 1,000. Now, I'm going to make it into decimal. I know I don't normally do this, but I think it'll be easier to see for you. So 3/10 is actually 0.3. 3 100ths is 0.03. 3 1,000ths is 0.003. So if I add those all up, what do I get? I get 0.333. All right? It is 0.333 when I add those up. Okay. All right, let's look at the difference between this one. Now I'm actually going to find the sum. All right, so we're going to go forever and ever. So now I'm going to go from 1 to infinity of 3 over 10 to the I. This might take a while.
Yes.
So I substitute in 1. What do I get?
It's 1/3.
It might be. Don't give it away to everybody, Joseph.
No.
All right. So I substitute in 1. What do I get?
Let's see what it ends up being.
I get 0.3. You're right. All right. So then, what's my next one? 0.03. And then my next term is 0.003. And then my next term is 0.0003. Which is really what? I don't need to keep going. What do we know it is? 0.3 repeating, or also known as 1/3. All right. Now, does 1/3 actually exist? No, it doesn't exist. Why not? It never stops. You can put another one on it. All right, you can put another one on it. And another one on it. All right. Cade might make money someday. Here we go.
A deposit of $5,000 is made in an account that earns 3% interest compounded quarterly. The balance in the account after n quarters is given by blah, blah, blah. Write the first 3 terms of the sequence.
All right, so we're going to write the first 3 terms of this sequence. Now, what's my first one going to be? A sub what? A sub 0. It's going to make me start out A sub 0. So we're going to substitute in 0. And so I end up with 5,000. All right. And then I'm going to substitute in A sub 1. 37.50. Why am I going to round to 2 on all of these? Because it makes sense. All right. All right. And then we're going to substitute in 2. So A sub 2. Evan, what'd you get? 28 cents. All right. Pretty good. All right. Part B, it says find the balance after 10 years. So what do we substitute in? Nope. We substitute in 40. Why do we substitute in 40 after 10 years? It says 10. Because it's quarterly. All right. So n would equal 4 times the 10, so it would be 40. So now I need to find A sub 40. And how much money we got? All right, fantastic. All right, pretty good. All right. I need another reader. Thank you so much, Mariah, for volunteering.
In the years 1980 through 2007, the resident population of the United States can be approximated by the model A, where AN is the population in millions and N represents the year with N equals 0, corresponding to 1980. For the last 5 terms of this finite sequence, which represents the U.S. population for the years 2003 through 2007.
All right, so we're not going to find all of them. However, let's just talk about 2003. What would N be for 2003? 23. All right, because 1980 starts with 0. All right, and so 2003 would be N equals 23. So all we're going to do is just find A sub 23. But really, this question asks you to find A sub 23, A sub 24, A sub 25, so forth. All right, so just substitute in 23. And what do we get? 241 million people. All right, pretty good. All right. All right, I want to do another one from your homework before you even start homework. All right, so we're going to have the 3 minus 9 plus 27 minus 81 plus 243 minus 729. All right, and we're going to be asked to put this in summation notation. All right, we're going to be asked to put that in summation notation. So, how many terms do I have? I have 6 terms. All right, so we got this as 6 terms going on. So my upper summation is going to be 6 if I start at 1. All right, so that's how you find your lower and upper bounds, okay, or your lower and upper indexes. All right, so Now I need to write the rule. All right? And so this is kind of going back to our first part of chapter 9. So what do we need to do to write our rule? What's it doing? It's switching from positive to negative. So how do we take care of that? It'd be negative 1 to the power of n plus 1. All right? So I took care of my negative that way. So then what? Now what's it doing? It's going from 3 to 9 to 27. What's it doing? It's multiplying by 3. And if it's multiplying, it's really what? Exponential. So then it'd be 3 to the power of n. Now, do I have to go anywhere if like I need to add anything or subtract anything? No. If we substitute in 1, guess what we get? We get 3. If we substitute in, let's say, 5, we should end up with 243 as well. All right. Hello.
Is it possible for you to do an example?
Seed.
Ooh, it's a dolphin.
9.1b. All right.
Whoa,